All right, let's go ahead and use the whole idea of water displacement, um, where we collect a gas from a chemical reaction through the displacement of water. And so this is the general concept of it, where we have some sort of chemical reaction occurring where there is a production of gas. The gas goes up and through the tube here, and when it comes out of the tube, it gets collected up inside of this test tube or container. And what ends up happening is as the gas goes up, it's pushing this water down, and so the water gets displaced. And then what ends up happening is you end up with a bunch of gas in here that you've collected. Now the reality is that there is not 100% of whatever gas that you're collecting in there, because water does evaporate and there's going to be some amount of water pressure in here. And the whole idea of these next couple problems is that whatever the pressure of the gas is in here and whatever the pressure of the water is in here, those pressures added together will be the total pressure within that little area right there. And so what we're going to try to do is we're going to try to use those partial pressures to figure out a total pressure, or we're going to use a total pressure to figure out the partial pressure of a gas. And so let's go ahead and take a look here. Now, when you're doing this, there is this reference table. This is something that if we're ever going to do something in this class, you'll be given this table. And essentially, what it tells you is at whatever given temperature you're working with. For example, let's say we're at 10 degrees Celsius. The partial pressure of water is going to be 9.2 millimeters of mercury. So if we're at 25 degrees Celsius, the partial pressure of the water is going to be 23.8. And so we can look at this chart to figure out the partial pressure of the water depending on what temperature we're at. So oxygen gas is collected from the decomposition of potassium chlorate, and it was collected by water displacement. The pressure gauge and the temperature during the experiment were 731 millimeters of mercury. Now, real quick, this is going to be the total pressure, because the pressure gauge, whatever pressure gauge or pressure reading you're getting, that's going to be the total pressure. And it was happening at 20 degrees Celsius. What was the partial pressure of the oxygen gas? Well, again, this is being collected through water displacement. So there's oxygen gas in here, but there's also some H2O. So we have oxygen gas plus water vapor. I'm going to put G here to illustrate that it's a gas, and both of these are inside of this area right here. And so we know that whatever the total pressure is, it's going to be the partial pressure of the oxygen gas plus the partial pressure of the water. And what it specifically is asking for, it's asking for what is this? So we know the total pressure, which is 731 millimeters of mercury. Now, again, we're looking for the partial pressure of the oxygen gas, but to find that, you need to know the partial pressure of the water, and the problem doesn't give that to us. However, the problem does give us the temperature, and we can go back to this. We can say, oh, at 20 degrees Celsius, the partial pressure of water is 17.5. And so we can do that, and now it just becomes a simple subtraction problem where you take your 731 and you subtract your 17.5, and that will give you the partial pressure of oxygen gas to be 713.5 millimeters of mercury. These might be the easiest problems of this whole class. All right, so let's go ahead and move on to the next one. It says some hydrogen gas is collected over water, and it's giving us 20 degrees Celsius. So it says the level of the water inside and outside of the gas container are the same, and the partial pressure of the hydrogen is 742.5. It's saying what is the barometric pressure at the time of the gas. Now, what this is asking for, when it says what is the barometric pressure, this is asking for the total. So again, we know that the total pressure is equal to the partial pressure of the hydrogen gas, plus we know that it's being collected just like this. It's being collected inside this tube here through water displacement. We know that there's some water in there as well. And so what it's asking for in this situation is asking for the total. And so this is also really easy, because all we need to do is we need to take the partial pressure of the hydrogen gas, which it gives it to us right there, and we have to add whatever the partial pressure of this is, which again, it's at 20 degrees Celsius. So if we look at our chart, it happens to be the same thing as last problem, 17.5. And so we add 17.5. And when we type that in the calculator, we end up getting 760 millimeters of mercury. And so this is, again, millimeters of mercury. And that's all there is to it. Now, just a quick note, 760 millimeters of mercury happens to be equal to 1 atmosphere pressure. So wherever this is occurring, that means that that they must be at sea level or something like that, because there's 1 atmosphere pressure on the outside. So just an interesting side note. But that's all there is to it. Now, this concept is being applied to water displacement, but you can apply this concept to other things as well. So you can, like in the air around us, there's nitrogen gas, oxygen gas, and carbon dioxide. And so we know that the total pressure of the air around us is going to be equal to the partial pressure of the nitrogen gas, plus the partial pressure of the oxygen, plus the partial pressure of the carbon dioxide. And there's actually a whole bunch of other gases too. Like there is some amount of water vapor in the air around us. There's some amount of other things as well. But the main ones are these 3 right here. And so again, it's just any sample of gas, if you add up their partial pressures, will give you the total pressure. So that's all there is to it.